Hello everyone, we will be starting in a while. So let us start with the session now. So this is the session 5 of rapid revision for JEE mains, and here we start with the questions. So question number 1, the element which exists in liquid state for a wide range of temperature and can be used for measuring high temperature is. Now we know that the element which exists in liquid state is mercury, right? Mercury is basically the metal which exists in a liquid state in your thermometers also. But except mercury, if you consider the element which is existing in the liquid state for a wide range of temperature and is used for measuring high temperature is gallium, right? If you look at the basically melting point and boiling point of gallium, its melting point is 29.76 degrees Celsius and boiling point is 2400 degrees Celsius, right? So because of its high melting and boiling point, it can be used for measuring high temperature, and it is also present in liquid state. Here if you see that boiling point is very high and melting point is approximately equal to 29.76 degrees Celsius. Next, if you consider a compound X of boron reacts with ammonia on heating to give another compound Y, which is called inorganic benzene. Now this is very important. Inorganic benzene is basically what? B3N3 H6. This is known as what? Basically inorganic benzene. Okay, so the compound X can be prepared by treating BF3 with lithium aluminium hydride. Now this is very important. If you treat BF3 with lithium aluminium hydride, instead of fluorine you get hydrogen here, right? And next it says the compound X and Y are represented by the formula. Now BF3 plus lithium aluminium hydride is giving you X, and X on reaction with ammonia basically is giving you what? Inorganic benzene. Inorganic benzene. So if you consider that what are basically X and Y, here if you see X is B2H6 and Y is B3N3H6, right? So this is known as what? Basically inorganic benzene. Inorganic benzene, which is formed by reaction of B2H6 with ammonia, right? So X is B2H6 and BF3 plus lithium aluminium hydride will give you diborane, that is B2H6, and diborane on reaction with ammonia will give you inorganic benzene, that is basically B3N3H6. Now if you draw the structure of inorganic benzene here, this is the structure of inorganic benzene. Alternating boron, nitrogen, boron, nitrogen, boron, nitrogen here, and here boron and nitrogen both are sp2 hybridized, both are sp2 hybridized, and if you compare it to C6H6, that is the benzene basically. This is the normal benzene and this is the inorganic benzene. This is known as the organic benzene, right? So this is C6H6. So if you compare the aromatic character of inorganic benzene and that is B3N3H6 and C6H6, this B3N3H6, here it will be hydrogen basically. Yeah, so B3N3H6, if you take, it is less aromatic than that of the organic benzene. This is very important, right? Because here if you see carbon, 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 carbon. So delocalization is taking place here fully, but here partial delocalization of electron takes place. So aromatic character of inorganic benzene is less than that of the organic benzene, that is C6H6. So this was all about inorganic benzene. In the structure of diborane, all hydrogen atoms lie in one plane and boron atoms lie in a plane perpendicular to this plane. Second says 2 boron atoms and 4 terminal hydrogen atoms lie in the same plane and 2 bridging hydrogen atoms lie in the perpendicular plane. Third says 4 bridging hydrogen atoms and boron atoms lie in one plane and 2 terminal hydrogen atoms lie in a plane perpendicular to this plane and all the atoms are in the same plane. So, to determine the basically correct option of this question, you have to draw the structure of diborane. So, this is the structure of diborane here. These B1, B2, H3, H4, H1, H2, that is 1, 2, 3 and 4 are called the terminal hydrogens. They are called the terminal hydrogens, while H5 and H6 if you take, they are known as the bridging hydrogens. Bridging hydrogens, right? So, B1 and B2 and H1, H2, H3, H4 are present in one plane and H5 and H6 are present one above the plane and one below the plane respectively, right? So, the answer for this particular question will be that 2 boron atoms and 4 terminal hydrogen atoms, that is B1, B2, H1, H2, H3, H4 are lying in the same plane, and if you take H5 and H6 which are the bridging hydrogen atoms, they lie in the perpendicular plane. Okay. Question number 4. Sea divers go deep in the sea water with a mixture of which of the following gases? Now we know that in the sea water the oxygen content is low. So basically sea divers take the cylinders which are containing oxygen and helium, right? So the answer for question number 4 is A, that is oxygen and helium. Sea divers take along with them deep in the sea water. Question number 5. The shape of xenon O2F2 molecule is. Now see here, there is a difference between the geometry and shape. In shape we will not consider lone pair basically, right? In shape we don't have to consider the position of the lone pair. Now draw the structure. Xenon, it is having how many electrons? 8. 1, 2, 3, 4, 5, 6, 7, 8. Fluorine forms single bond. 1, 2. Oxygen forms double bond O, and 1 lone pair. So how many? 1, 2, 3, 4, 5. That means trigonal bipyramidal structure. So this will be equal to, lone pair is on the always equatorial side according to the Bend's rule, right? And this one you will get it as fluorine, fluorine, double bond O, right? Or to make it more clear, we'll draw the structure this, right? So this is the structure. Now the geometry is trigonal bipyramidal, but lone pair of electrons are not taken while determining the shape of the molecule. So omit the lone pair, you can see the seesaw type of structure, seesaw type of shape. So the answer for this particular question will be D, that is seesaw. Question number 6. Which one of the following reactions of xenon compound is not feasible, right? So xenon reactions with fluorine, oxygen and structure of xenon and structure of xenon compounds are very important from the examination point of view, right? So while doing the P block, just remember the structures of xenon compounds with fluorine and oxygen respectively, and also the reactions. Okay, so here if you see the D option, that is xenon O3 plus HF is giving you xenon F6 plus water. What happens here is that xenon F6 on reaction with water gives the backward direction reaction, that is it again forms xenon O3 plus HF. So this reaction is not feasible because the product themselves react to form xenon O3 plus HF. Question number 7. This is from chemical bonding. So list 1 and list 2 need to be matched. So there are the structures basically here. So xenon F4, if you take, how many electrons? 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. Fluorine, single bond it will make 1, 2, 3, 4. 2 lone pairs of electron. So 1, 2, 3, 4, 5, 6. That means it will acquire a octahedral geometry, lone pair here, let us say lone pair here. But if we don't consider the lone pair, basically the shape comes out to be what? Square planar. The shape comes out to be what? Square planar. So for A, 3 is the option. For A, 3 will be the option. Come on to xenon F6. Xenon 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, and this one is 7. So this is very important that xenon F6 has a distorted octahedral structure. It is very important. It will have the structure like this. A octahedral structure basically, and the lone pair is somewhat present here, right? So it is a distorted octahedral structure. So for B, first is the option, right? Now next come on to xenon O3. How many electrons? 8. 1, 2, 3, 4, 5, 6, 7, 8. Now oxygen will form double bond. 1, 2, 3. Draw this closer, electrons, and one lone pair, right? So here if you see, what is the geometry basically? Pyramidal geometry. Here, here, here. So xenon O3 is trigonal pyramidal. So for C, fourth is the option. Now come on to xenon O4. Again draw 1, 2, 3, 4, 5, 6, 7, 8. How many oxygens are there? 4. So each will form double bond. 1, 2, 3, and this one is 4, right? So it will have a tetrahedral geometry, somewhat like this. So answer for D will be what? 2. So you can see here that A was 3, B was 1, C was 4, and D was 2. So the answer for this particular question is D. Question number 8. Which of the following is the strongest acid, right? So if you come on to the oxo acids of chlorine, basically the greater number of oxygen content, more is the stronger acid. This always remember that for oxy acids of chlorine, you can take that the number of oxygens are greater or the oxygen content is more, therefore the acid will be more stronger. So here if you see 1, here if you see 3, here if you see 4, here if you see 2. So C will be the option for this particular question because it is having more oxygen content, so it will be the strongest acid. Okay. Draw the structure of ClO3OH. It will be what? Cl, OH and then double bond O, double bond O, double bond O. Okay. Question number 9. Of the 4 elements, the one having maximum electron affinity. See, there is a difference between electronegativity and electron affinity. Electronegativity is what? Basically attracting the shared pair of electron towards yourself. Electron affinity is what? Basically in the gaseous isolated atom, what is the tendency of that particular atom to gain an electron is known as electron affinity. So electron affinity is basically in the non-bonded state, while electron negativity, if you see, it is in the bonded state. So electronegativity, if you consider, fluorine is maximum, but electron affinity, if you consider, see, fluorine and chlorine, if you see, it has more tendency to attract electrons. But what happens when it converts into F negative? Because of its smaller size, electron-electron repulsion takes place, right? And when the electron-electron repulsion takes place, it becomes unstable. While that of chlorine, if it gains one electron, let us say, so electron-electron repulsion is not as that much as of compared to fluorine, because the size of chlorine is greater than that of fluorine. So electronegativity, fluorine is greater, and electron affinity, if you see, chlorine is greater, right? So of the 4 elements, the one which is having the maximum electron affinity is B, that is fluorine. Question number 10. Antichlor is a compound which absorbs chlorine, which removes chlorine from a material, which liberates chlorine from bleaching powder, which acts as a catalyst in the manufacture of chlorine. Now, the answer for this particular question, if you see that what are antichlor compounds? Antichlor compounds are is a compound which remove unreacted chlorine from a material. For example, if you take this hypo Na2S2O3, right? So what is the oxidation state of sulfur here? Let us say +2 plus 2x minus 6 will be equal to how much? 2x equals to 4. So x will come out to be +2. So the oxidation state of sulfur here is +2, and the oxidation state of chlorine is what? 0 basically, right? Now what happens? It oxidizes itself. Sulfur oxidizes itself to find out the oxidation state here. It will come out to be +6, while it reduces chlorine into -1, right? So antichlor compounds such as Na2S2O3, they react with, or they remove basically the unreacted chlorine from the material. Okay. Bleaching powder on standing forms a mixture of, see, for this you have to remember the formula of the bleaching powder. That what is the particular formula of bleaching powder? So here if you see, calcium oxychloride is known as the bleaching powder. CaOCl2 is known as the bleaching powder. Now on standing, it decomposes into CaClO3 whole twice and calcium chloride, right? So it is called auto-oxidation. It is called auto-oxidation. That means bleaching powder on standing forms a mixture of option D. Okay, so these particular reactions basically they are very important from the examination point of view. That is why we tend to include in the rapid revision of JEE mains, right? So you don't have to learn all the equations of P block. There are certain equations you can refer to the material itself, and you must be gone through the classes basically, right? That which reactions of P block are important, only that reactions you need to study, okay? And the structures are very important from the P block. Even from the S block also, S and P block, if you see, structures are very important, right? Boron compound is very important. Boron compounds, nitrogen compounds is very important. Phosphorus compounds are very important. So these three you have to learn it by heart, especially their structures. And xenon compounds, if you see, interhalogen compounds. So you have to study selectively basically, okay? Question number 12. By the action of conc HCl or concentrated HCl on potassium chlorate, we get the mixture of gases as. So what is basically potassium chlorate, KClO3. On reaction with conc HCl, it produces KCl, Cl2, ClO2. Now the mixture of Cl2 and ClO2 is known as euchlorine. Euchlorine. Sorry. So this name also you have to remember, right? So KClO3 on reaction with HCl will give you what? Cl2 plus ClO2 mixture. So the answer for this particular question will be C. Now these questions are important from the examination point of view. Br2 plus CO3 2 minus plus H2O is giving you Br negative, BrO3 negative and bicarbonate ion. Now it is asking that bromine is oxidized, carbonate is reduced, bromine is both oxidized and reduced, bromine is reduced and water is oxidized, bromine is neither oxidized nor reduced, right? So here if you calculate the oxidation state of bromine, it comes out to be 0. Here if you calculate -1, here if you calculate x minus 6 equals to -1, that will be equal to what? Basically +5. So here you can see that from 0 it is going to -1 and from 0 it is going to +5. That means it is undergoing reduction here. And here it is undergoing oxidation. That means bromine is both oxidized and reduced. So the answer for this particular question is B. I hope you are able to get all the questions. Some part of the P block and S block, if you see, you have to mug up the reactions, but some part you can apply the oxidation reduction tricks also, right? FeCl3 solution on reaction with SO2 changes to. Now here if you see the reaction basically, that FeCl3 on reaction with SO2. See, FeCl3, the iron is in +3 oxidation state and it is forming FeCl2, that the iron is in +3 oxidation state here and +2 oxidation state here, right? So you can remember it this way, then FeCl3 on reaction with SO2 changes its oxidation state. For example, if you see that Fe, the more common oxidation states are what? Basically Fe3 plus and Fe2 plus. So Fe3 plus is already present, right? So you can rule out the two options, that is B and C basically, right? Here also it is +2 oxidation state and here also it is +2 oxidation state. So accordingly you can eliminate the options. You can use the elimination method this way for certain questions, right? So here if you see FeCl3 converts into FeCl2, that means iron from +3 converts into Fe +2 and SO2 converts into H2SOO4. Okay, so here if you see the oxidation state of sulfur, it will come out to be how much? +4. Here if you see, it will come out to be what? +6. That means oxidation of sulfur is taking place and reduction of iron is taking place. Okay. Question number 15, again from molecular orbital theory, a very important question. For oxygen, if you see, draw the MOT, 1s, sigma 1s, sigma star 1s, 2s, sigma 2s, sigma star 2s, then you will get sigma 2pz, pi 2px 2py. These are the anti-bonding and these are the bonding basically, right? Here you can draw the p orbitals, 3, and here also 3. Now you can fill up the electrons. So O2, if you see, what are the number of electrons? 8 plus 8, that is equals to how much? 16. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So how many electrons are there in the, what is the bond order basically? The formula for bond order is half into bonding electrons minus that of the anti-bonding electrons, right? So this is the formula for bond order. Now count the number of bonding electrons: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be half into 10 minus, what are the number of anti-bonding? 2, 3, 4, 5, 6. 6. That will be equal to 2. So the bond order for O2 will be what? 2. Now you calculate it for plus, that means one electron will be removed. So from anti-bonding, one electron has been removed. Now the bond order will come out to be half into 10 minus 5. That will be equal to how much basically? 2.5. So for O2 plus, the bond order is coming out to be 2.5. For O2 minus, if you see, that means oxygen, you add one electron in the anti-bonding, right? So this will become how much? Half into 10 minus 7, that is equals to 3 by 2, that is equals to 1.5. So for O2 minus, it will come out to be 1.5. Now for O2 2 minus, 2 electrons you have to add it to O2. So this will become half into 10 minus 8, that is equals to 1. Okay, now you can arrange. So what will be the arrangement here? O2 is having 2, O2 plus is having 2.5, O2 minus is having 1.5, and what else? O2 2 minus is having 1, right? So O2 plus greater, then O2 greater, then O2 minus greater, then at the last O2 2 minus. So if you compare the options now, the answer for this particular question is B. Okay. Basically, you can also remember the trick that if you remove electrons from the anti-bonding orbital, if you remove electron to the from the anti-bonding orbital, there is a increase in the bond order. Increase in the bond order. While if you see the anti-bonding orbital, if you add electrons to the anti-bonding orbital, there is a decrease in bond order. Decrease in bond order. I hope it is clear. Question number 16, if you see, sulfur-sulfur bond is not present in. Now this you can write it down as H2S2O4. This you can write it down as H2S2O5. This you can write down as H2S2O3. This you can write it down as H2S2O7. Now we'll draw these structures one by one, and we'll find out that in which of the following compounds the SS bond is not present. So here if you see, first O3, yeah. So first we have to do H2S2O4. Yeah, so here if you see the structure, H2, S2, O4, 1, 2, 3, 4, right? So this is the structure of H2S2O4. So sulfur-sulfur bond is there. That means this option is incorrect. Now move on to H2S2O5. So here if you see, 2 sulfur, 2 hydrogens, and 1, 2, 3, 4, 5 oxygen. Here also sulfur-sulfur bond is present. So this option is also incorrect. H2S2O3. Here if you see the structure, H2, S2, 1, 2, 3, O3. So this is the structure for H2S2O3. Here also a sulfur-sulfur bond is present. That means this option is also incorrect. Now come on to option number D, that is H2S2O7. So yeah, so H2S2O7. So it will be equal to, the structure will be sulfur, 2 sulfur, 1, 2, 3, 4, 5, 6, 7 oxygen and 2 hydrogen. So here if you see, there is no SS bond, rather there is a SOS bond, right? So answer for question number 16 should be D. So basically you have to remember all the structures of sulfur, phosphorus and boron compounds. You have to remember these structures. Xenon, again I am repeating, you have to remember these structures. So pay attention to them, okay? Just a second. Okay. Question number 17. Concentrated nitric acid upon long standing turns yellow-brown due to the formation of. If you have been attending our P block session, I have continuously repeated that the oxide of nitrogen that is yellow-brown in color is NO2. This is very important, right? So again, if you even don't remember that what is the product obtained when nitric acid basically decompose on long standing, you can just guess out the answer from this particular fact, that which of the oxide of nitrogen is yellow brown in color, right? So HNO3, if you see, decomposes on long standing and converts into NO2 plus H2O plus O2. So this is the oxide that is obtained. So answer for question number 17 is B. Question number 18, if you see, the deep blue color produced on adding excess ammonia to copper sulfate is due to the presence of. Now this is very important. See, we tend to remember that it is copper 2 plus. Right, we tend to remember that the complex is of copper 2 plus, but we forget the number of ammonia ligands here, right? So if you see here that copper sulfate on reacting with excess ammonia forms a square planar complex, that is copper NH3 2 plus, not 6, not 2, rather a square planar structure with 4 ligands. So the structure is somewhat like this. Somewhat like this is the structure, 2 plus. Okay, so 4 ligands of ammonia are there with a copper 2 plus ion, and this is blue in color. Question number 19. Chemical A is used for water softening to remove temporary hardness. Now we know that temporary hardness is caused due to the bicarbonates, right? A reacts with Na2CO3 to generate caustic soda. So basically you have to remember the chemical formula of quicklime, slicked lime, caustic soda, bleaching powder. These you have to remember. So A reacts with a base to generate caustic soda. When CO2 is bubbled through A, it turns cloudy. What is the chemical formula of A? Right. So here if you see that if the temporary hardness is because of calcium bicarbonate, basically it reacts with calcium hydroxide to give calcium carbonate plus water, right? The second reaction, if you see, it says that it reacts with Na2CO3 to get caustic soda. So what is caustic soda? Basically NaOH, right? So calcium hydroxide on reaction with Na2CO3 gives caustic soda. Now see here, the third point is very important, and it is a general reaction that we should all know. When CO2 is bubbled through A, it turns cloudy. Now this is very important reaction that you have been learning from class 10th, I guess, that calcium hydroxide on reaction with carbon dioxide generates milkiness, which is due to the formation of calcium carbonate, right? So now you can easily guess the compound by one statement only, that when CO2 is bubbled through A, it turns cloudy, right? So the answer for question number 19 is what? Basically C, that is calcium hydroxide. Question number 20. Thermal stability of alkaline earth metal carbonates decreases in the order. Now this is very important. See, if you see carbonate here, CO3 2 minus, right? It is a polyatomic ion, polyatomic anion. So in this case, you can remember that in case of polyatomic ion, the thermal stability of the metals increases down the group, increases down the group. Right. So here if you see, these are the group 2 elements. What are group 2 elements? Beryllium, magnesium, calcium, strontium, barium. So beryllium is not there. So basically if you see, because carbonate is a polyatomic ion, and for a polyatomic ion the stability of the metal carbonates increases down the group. So here barium carbonate will be more stable, then strontium carbonate, then calcium carbonate, and then magnesium carbonate. So answer for question number 20 is A. Okay. I hope you have gone through all the questions well, and practice more and more questions, right? And basically you can take out the previous year questions, give it a read first, and then revise the concepts to the questions. Okay, so that's all for today. Thank you to all.